Hey everybody, and welcome back to Algebra 2 Online. So today marks the first video in our new unit. It's a unit on exponential functions, which hopefully you kind of remember from Algebra 1, and something called logarithmic functions, which you aren't supposed to know at all, which are really just the inverses to exponential functions. But more on that in a bit here. So to start off, this is something that I actually would want you to go and kind of play around with. So if you use Desmos, you can do this with like a bunch more functions if you want to, but I think you'd get the idea with this. So if you go plug these exponential functions into Desmos, I want to see if you can come up with basically a hypothesis about when exponential functions grow versus when they decay, okay? And I'm obviously going to explain it here in a second, so I would recommend you pause the video, plug these into Desmos, and just see when do exponential functions get bigger over time and when do they get smaller over time. So 1, 2, 3, I'm going to explain it now. So hopefully what you saw was that so we'll say like an exponential function like b to the x, like this. If b is bigger than 1, that's a bad greater than symbol, b is bigger than 1, that's when you should have seen it grows, right? So this one should grow, 20 to the x should grow, even 1.1 to the x should grow. This one is going to grow really, really, really slow, whereas this one grows really, really, really fast. But they both grow, okay? And then if b is between 0 and 1, okay, any of those fractions in there, that's when it's going to decay, right? And it's actually true that the same results happen for logarithms. So what you're about to see is that logarithms have a base to them too, and when the base is bigger than 1, logarithms are going to grow, and when the base is between 0 and 1, logarithms are going to decay, okay? These are also questions that hopefully you can kind of see from this, but all of these graphs, they kind of have some similarities to them. So what you should see for the ones that grow is they kind of look like this, whereas the ones that decay kind of look like that. And there's some kind of nice similarities and that have to do with like domain and range that I want you to see here. So the domain for these is all reals. There's absolutely nothing wrong with doing like 2 to the 0, right? That's just 1. 2 to the negative 1 is 1/2. 2 to the 3 is a nice number. It's 8, right? Like, there's nothing wrong with any of these x's that you plug in. It's perfectly fine. The range, though, is going to be bounded, okay? So for all these exponential functions, the range you should see is always basically greater than 0. And that's just because, if you do, any of these bases to a power, right, you're just not going to be able to get a negative number. Like, you also won't be able to get 0. The only base that, you can get to 0 would basically be 0 to a power, right? But 0 to a power is just a constant function of 0. And 0 to the 0 is actually also something really weird. So that's something that we call an undeterminate form, or indeterminate form, sorry. So we don't even allow the base to be 0. So you can't even get 0 because the base is never considered to be 0 in these functions. And there's also something weird that happens if the base was negative. Like, you can't get it down here because you don't have like negative number to a power. And that's because if you took like negative 2 to the x, okay, let's just kind of do this. Let's just map out 1, 2, 3, 4. So negative 2 to the 0. 1, 2, 3, 4. Negative 2 like this, to the 0, right? Anything to the 0 power is 1, so that would be there. -2 to the 1 would be down here at like -2, right? -2 squared is like up here at 4, right? And then -2, so you can kind of see, and I didn't give myself enough room, but if, here, let's make it actually a little bit closer. Let's say, so let's say it's ticked off. The scales are just going to be different, but it helps to kind of see it. So, we have 1 there, and then we have -2 there, then we have 4 here. 1, 2, 3, 4 is about right there. So you can kind of see that you get this like pinball effect, right? And the weird thing about this graph, if you do a negative base, it's not going to be defined. It's just, it doesn't make sense. So when we do exponential functions, all right, one of the most important things to remember is that the base can't be 0 and the base can't be, I'll just write it, negative. So your base is always greater than 0, right? It can be really, really large as you want it to be. It can be like, 4,000,007, but it can't be negative 4,000,007. And because of this stuff, you never get an exponential function that would have a range down in here. All the range values are going to be positive. So actually, kind of built off of last unit, the x-axis is actually acting as an asymptote for the graph. So that is actually true. As you go to the right, like for a decay one, right, it just keeps getting closer and closer and closer over here. And as you do a growth one, the really, really small numbers in the x will get you really close to 0, but they won't really get you to 0. Those are just some of the kind of really fundamentals of exponential functions. They grow when the base is bigger than 1, decay when the base is between 0 and 1, and defined for all reals, and the range is greater than 0. And you can't do these two things. They don't make sense. These three examples here are actually just real problems that we will do in this unit. And what we're basically going to have to kind of first understand is, even what these exponential and log functions are. There's a lot to kind of just unpack there, which I'm going to actually start doing on the next slide here. But then we have to know how to start working with equations with them and stuff like that. So, the exponential stuff that you learn in Algebra 1 is really just kind of like basic like growth sort of stuff. So you don't really have the chance, you don't have the tools yet to actually solve much, but in Algebra 2 you're finally going to learn how to really solve some real application problems. Exponential and logs just show up literally all over the place. There's all sorts of these like radioactive isotopes in the world, and it's something your science teachers can explain a little more, but basically there's a connection between literally the sun, that's what this picture is trying to show you, and the molecules on Earth, and they're sometimes like electrons can sort of leave an atom, and then you get radioactive isotope, and that's a very hand-wavy definition. There's a lot more to it, but these show up all over the place, just naturally occurring in the world, and not naturally too. We can kind of create these. So there's a bunch of exponential decay, really, problems with these ones that we will actually do. All three of these are problems that we will literally do in this unit. But in order to do that, we need to understand how to work with logarithms first. So we're going to build towards that in the beginning here. And this is actually another radioactive decay thing. Carbon-14 is very famous. One of these radioactive elements. Potassium-42 is the name of another one here. The number at the end relates to the electrical structure, electrons in the shells around the atom. But another very, and those are the kind of things that we won't talk about too much. That's very much a science thing. Another very common application is like exponential growth with like things like bacteria and stuff. So, this is something that this year is all feel like people think about is growth rates of different things, and you can analyze COVID with exponential growth and all sorts of stuff. If you go into business, exponential stuff shows up in stocks, and you need logarithms then to understand how to solve problems with them. So they're just literally all over the place, and we will do some pretty basic applications, but we will do some applications in this unit for exponential growth and decay and that kind of stuff. But today the plan is really just to understand the beginnings of what a log is and how to graph basically exponentials and logs. So first and foremost, probably one of the most important things to know here is the inverse to an exponential function is a log, okay? So if exponential functions take like x to y, right, then logarithms are going to take, and we do abbreviate them sometimes just log, and I'm going to actually talk about some special logs that are found on your calculator that we will use, but one of them that you'll actually see on your calculator is literally written just log like this. But this is, kind of the picture based off of our chapter 6 stuff. This is kind of the way you want to think about it. Exponentials take you from here to here. Logs will unpack that and go from here back to here. So, anytime you have an equation in math with an exponential, you're going to need a log to solve it. If you have a log equation, you'll need an exponential to solve it. They're the, tools that undo each other, basically. And I do want to talk here about like the kind of structure of them a little bit. So a log, like exponentials are fairly straightforward. Like if you have some sort of function, g of x equals 70 to the x, we kind of understand that already. It's just a number 70, and you can plug in all sorts of numbers up here. 70 to the first is 70, 70 to the negative 1 is 1 over 70, 70 to the 0 is 1, 70 squared is something big that I don't know, that sort of stuff. Actually, it's not that hard, except just squares 7. But we understand exponentials, I think, well. What we probably don't know, and no reason you should, is logarithms. So if you, this is kind of I'll put it out, I guess, in words here first, and then I'll explain it. So this is sort of the structure of a basic logarithm, and it looks kind of weird, but a logarithm has a base, and we put the base as like a subscript. We actually write it below the main line, and instead of writing logarithm, we write log, okay? Or there's going to be another special one that I will teach you about. So sometimes this is a little different, but for today, it's just going to be log, okay? And then we have the input up here. So, and the easy thing, if you wanted to do the inverse to, say, g, all right? The inverse is a logarithm. You put log, and the really easy way to write it, if g of x is 70 to the x, the inverse, you just match up the bases. So we have 70 down here, and then we'll just put an x right there. So literally, if you go to Desmos and you type 70 to the x and log base 70 of x, that's how you read that. Maybe write that down. So that's how you would read it. This is log base 70 of x. These two will be symmetric with the line y equals x. They're inverse functions. And if you do, 70 squared, you get 4,900, right? And I promise you, if you do log base 70 of 4,900, right, we plug in the output, right, it will take us back to the 2. So, 2 into the exponential gave you 4,900. 4,900 into the log would send you back to 2. It will create that loop that we've seen with inverses like that. And we call that the base, we call that the input, that's still the output, that kind of stuff. But that's the basic structure of them. This is probably one of the most important sort of slides, I guess, in this video, and really this unit in general, because it's the one where I'm going to lay out all the basic properties of exponentials and logs. So mind you too that all these properties are for the basic exponentials, so b to the x, where b is greater than 0, and log base b of x where b is greater than 0. I'm not getting into function transformations here or any of that sort of stuff. So this is your basic exponential here and your basic log, right? So, and I have a few pictures of them for each one, so we can kind of use that to answer these questions. But no matter what exponential you have, all of them are going to go through 0, 1. And that's just because anything to the 0 power is 1, right? 10 to the 0 is 1, 3 to the 0. The only weird one in the world is 0 to the 0, because we don't know, should it be 0 or should it be 1? It really is this thing called an indeterminate form. And there are just things like this in math. There's not a lot of them, honestly, but there's a few things in math that we just don't know the answer to. And we probably will never know the answer to it. We don't know if this should be 0 or if this should be 1. It'd be weird to be 1, right? Because how would you get something from nothing? But if it still is nothing, then it breaks all this sort of stuff, right? And if you need a refresher on why anything to the 0 power is 1, go back and look at my video on the properties of exponents. It was like 2 units ago, basically, we did it. So anything 0 is 1, so they all go through that, which is nice, okay? We already said this thing about the domain, but domain is all reals, and the range is greater than 0, okay? And I briefly said it, but there is an asymptote involved in these graphs, and it really is the x-axis. So it's, y equals 0. You just can't get there, but you get really, really, really close to there, right? The reason you get close is if you do things like, so 10 to the negative 1, and then let's say we do 10 to the negative 100, and then 10 to the negative 1,000. I think this will help get the idea home. This is 1 over 10. This is 1 over 10 to the 100. This is 1 over 10 to the 1,000, right? And you can see, like, these bottom values are getting bigger and bigger and bigger as you go left, right? So they're approaching, like if we talk about limits, their limiting value is, as you go to negative infinity, is 0. So these things do have an asymptote. Specifically, it's a horizontal asymptote. It's just the x-axis, y equals 0. So honestly, if you understand all those, then these should make sense based on inverse functions. So, every logarithm has a corresponding inverse exponential. So log base 2 of x is inverse to 2 to the x right here, okay? Log base 3 of x is inverse to 3 to the x. This one isn't over here, but because of that nice inverse relationship, right, you get a lot of these if you just understand how inverses work based off of this. So inverses reverse the direction, of like this kind of stuff. So instead of all of them going through 0, 1, all of them should go through 1, 0, which they do right there. And that's just because, like, the outputs here become the inputs here, and the inputs here become the outputs here, right? Likewise, the domain is related to the range, and the range here is related to the domain because everything's flipping because of the inverses. And so the domain should be now x greater than 0, and the range should be all reals. And you can see that in the picture too, okay? And there is an asymptote. It was horizontal before, but as inverses work, it'll flip sort of 90 degrees, and it'll become a vertical asymptote, and it becomes just the y-axis or x equals 0, whichever way you want to think about it. So it's right here. And this stuff right here should imply a very important thing to you. So whenever we get to the point where we're solving log equations, we are going to have to be worried about that domain, just like even roots. Even roots, it was, they could equal 0. Here you can't even get them to equal 0. They have a cutoff in the x, but with even roots, they kind of looked like these, but they didn't actually go down here. They just sort of ended right there, right? These ones do go down and down and down forever. But these ones never get to 0 because these ones never get to 0 in the range, right? So this is going to be an important thing to keep in the back of your head when we get to solving them, which is actually not super soon. But they are more annoying because of that cutoff in the x. All right, so this last thing I just want to do is just literally graph some exponentials and logs. And the way that I basically ask my Algebra 2 students to graph these things is start with, honestly, this part. So all of them go through one of these nice points, and what I would do is I would start with those, and then I would do my transformations on that point. So logarithms should go through 1, 0, right? And, based on this function, right, we have two transformations. This is a vertical stretch by 3, and this is a shift up 1, right? And so this does have to happen first. So basically we are at 1, 0, and then we're just going to multiply it by 3, like the output by 3, but the output is, 0, right? So if you multiply 0 by 3, it doesn't go anywhere. And then we have this plus 1, and so we basically just take my point down there, and we move it up 1, right? So that's kind of how the transformations work for that nice point, 1, 0. And then all I ask for in these kind of things is you use the base to help you figure out the general shape of it, okay? So if you remember back here, the growth or decay part all just comes from the base as well. So, and it's the same for logarithms. So if you do a base 10 logarithm, that's one that should grow. If it was a base 1/10, it would just decay through that point. But this one grows through that point. So, so we know that there's a vertical asymptote at 0, and we just kind of grow like that, and we just do some sort of sketch like that. That's perfectly fine. I literally am looking for 1 point. If there was some sort of left-right shift on this one, then this would also move with the graph, right? If you had shifted it like 2 to the right, then the vertical line at 0 would be now a vertical line at 2, right? But we haven't shifted it left to right. We've only really just done a scalar by 3 and shifted up 1. And this 3, it's just hard to see how it affects it. Like maybe the normal one was like something like that, but the 3 acts as a stretch and makes it a little steeper, something like that. But those are the things that I'm not really going to be able to kind of grade you on. So I wouldn't worry so much about how the curvature is. We just know that because there's a 10 there, it grows. And we know this we can definitely see is a shift of 1, 0, up, 1. And then, there's no shift left to right, so we still have that vertical asymptote. So that's kind of that one. For this one, exponential function, base 5, 6, we've got -1 in there, so we're shifted to the right 1, and then we got a +1, shifted up 1. So I'm going to start at 0, 1, exponentials, right? Start at that point, that's the nice one. And then you shift, you have a -1 in here, so that's a shift to the right 1. So now we're here, right? And then we have a +1, so then that point is going to shift here, right? So that will be my final point that I will deal with. So I'm just going to do that. We know that there is normally a horizontal asymptote, but because of the +1 here, right, it shifts that horizontal asymptote up 1, right? And then this thing is going to imply that there's decay, because B is between 0 and 1, the base. And so we just sort of fall down through that point and get close to that dotted line that goes through 1, right? This is y equals 1. And that y equals 1 is really dictated by that 1 right there. So that's really all I'm looking for. 1 point, a dotted line, and general shape. So maybe I'll even write that down. For our purposes, I need 3 things. A dotted line somewhere, a 1 point in the right spot. It's really not too much to ask. And then general shape. That's all I'm looking for, okay? If you can do those 3 things, you can, and you just use function transformations and the base to dictate the growth or decay part, and then, the dotted lines come with the graph, the corresponding graph, based on the shifts and things like that, you'll be all good. So your homework is really just doing stuff like this, and this is like very, very important to help you graph. Really all this stuff is important. So we will be in this unit for quite a bit. It's a pretty big unit. It's really, really important. If any of you want to take like AP chemistry and things like that, this kind of stuff shows up all the time there. I was in pre-med when I went to college, and pre-med, it's like just literally every day it felt like exponential growth and decay and logarithmic stuff and things. So very, very prevalent in the sciences. You'll see a lot with it if you go that route.